Welcome back, statisticians. I am here recording live in my secret bunker in Baldwin, Missouri. We're continuing on with section 4.4 and the multiplication rules, trying to calculate probability. And yesterday we talked a little bit about the or and the and we're going to continue on with the dependent events today, and we're going to try to find the probability of the compound events and conditional probability, and when they say what's the probability of at least one. So that's what we're going to try to cover today. Dependent events, they're basically events that are not independent. Two events are dependent if the occurrence of one of them affects the probability of the occurrence of the other. This does not necessarily mean that one of the events is a cause of the other. So that's all I have to say about that. So let's do some examples of dependent events. Drawing a card from a deck and not replacing it, then drawing a second card, because that lowers your possible cards when you're picking the second time. Being a lifeguard and getting a suntan. Now that one definitely has kind of cause-effect relationship, but the first one does not. Having high grades and getting a scholarship. Those are some examples of dependent events. Your book also has some extra examples of those. So let's talk about conditional probability. A conditional probability of an event is a probability obtained with the additional information that some other event has already occurred. So P, B given A represents the probability of event B occurring after it is assumed that event A has already occurred. And that's important. A already occurring, you just assume that it happened, alrighty? So it's read B given A. So the probability of B given A, this event given another event. Alright, conditional probability, here's some key ideas. We have to adjust the probability of the second event to reflect the outcome of the first event. And the probability for the second event should take into account the fact that the first event has occurred. We're just going to assume that it has occurred. Here's the multiplication rule part 2. Probability of A and B is the probability of A times the probability of B given A. Note that if A and B are independent, probability of B given A is really the same as the probability of B because it doesn't affect it. So that could be one multiplication rule. Here's the first example of finding probabilities of dependent events. Person owns a collection of 30 CDs, of 5 of which are country and 2 are selected at random. What's the probability that both are country music? Now you wouldn't think it's very high because only 5 out of the 30 are country. Since the events are dependent, pick one and pick 2. So probability that the first one's country, you can easily figure that's 5 out of 30. This one is the next one. Now, hang on to your hats. If you assume that you picked a country music CD the first time, you have to assume that that's happened. Then there's only 4 country CDs left out of a total of 29. So you had to subtract 1 from the top and 1 from the bottom. And then you multiply straight across. So you'd have 20 out of 870. Both of those are divisible by 10. So that's just 2 out of 87. I hope that makes sense. Let's move on. Worldwide Insurance Company found that 53% of residents of a city had homeowners insurance with the company. Of these clients, so that's important. They're saying these people who had homeowners insurance also had auto insurance with the company. So that's both things. If a resident is selected at random, find the probability that a resident has both homeowners and automobile insurance with the given company. So we're trying to find the probability of homeowners insurance times the probability of auto insurance given homeowners insurance. So they already actually gave you both things here. 53% had homeowners, that's the probability of homeowners, and then get out of those clients, so automobile insurance, given that they had homeowners to begin with, is P of H. So you just multiply those two together and you end up with 0.1431. That's your probability of homeowners and automobile insurance if you select a resident at random. Extend the multiplication rule to 2 or 3 more events in the following examples. So you can extend this out. Probability of A times probability of B given A times probability of C given A and B. So you just keep going down the list. Let's take a look at these. So if I get 3 cards from a deck. I'm not putting them back in the deck. So the probability of getting 3 jacks. Well, first off, there's 4 jacks in a deck of 52 cards. So it's 4 out of 52. Then I don't replace that card. So how many, we assume that this guy took place, that the first thing I got was a jack. So the next one is going to be only 3 jacks left in the deck out of a total of 51 cards. And we're going to assume that that took place as well, that we got another jack. So then there would only be 2 jacks left out of 50. So you have to assume that, the probability each one, the top goes down by 1, 4, 3, 2. And then each time we draw a card, the total number of cards goes down. When you multiply straight across, you get 24 out of 132,600. And putting that in lowest terms is 1 over 5,525. If I were you, hopefully when you're multiplying fractions, you can cross cancel. So for instance, I'd take the 4 into the 52, that's 1 out of 13, and 2 into 50, 1 out of 25, but you don't have to because you can use your calculators, and I'd probably get a decimal for this because most people know that doesn't correlate to them. So the next one, getting an ace, a king, a queen in that order. So getting an ace, there's 4 aces in a deck, so that's going to be 4 out of 52. A king, there's still 4. If we get an ace, that's no problem. We didn't pick a king, so it's 4 out of 51. And a queen is going to be 4 out of 50. We're picking cards, but remember, we always assume that the previous event took place to figure our probabilities. Multiply straight across, you get 64 out of 132,600, which is going to be 8 out of 16,575. Getting a club, a spade, and a heart in order. So clubs, there's 13 clubs in a deck. There's 4 suits in a deck. So that's going to be 13 over 52, or you can put 1/4 in lowest terms. And this one's going to be 13 out of 51 because we're assuming that we got a club, a club the first time, but we took a card out of the deck. There's still 13 spades left, and then there are going to be 13 hearts left, but there's 2 cards missing out of the total, so that's 50. Multiply straight across, you get 2,197 over 132,600. Put it in lowest term, bada boom, bada bing, you got it. Getting the 3 clubs. In this case, I'm going to let you finish this one for D. All right, another thing we can do is use a tree diagram to aid in finding the solution to probability problems when events are sequential. This is kind of a weird problem. When I look at this, it says box 1 contains 1 blue and 2 red balls. Box 2 contains 3 blue and 1 red ball. A coin is tossed to determine which box you're going to pick out of. If it falls heads up, box 1 is selected. If it falls tails up, box 2 is selected. Find the probability of selecting a red ball. So if I'm doing a tree diagram, remember I have 2 boxes. A box 1, box 2 that correlates to heads and tails. So I'm going to start out my tree diagram. When I flip the coin, I could either get a heads or a tails. If I get a heads, I'm going to pick from box 1. And so there's blue balls and red balls in there. I know you're thinking blue balls. Don't think that. It's terrible. You get your mind out of the gutter. And in this particular box, and so first thing we got to do is assign probabilities to each branch. So if we go along this branch, what's the probability that you're going to end up with heads? Well, that's going to be 1/2. So I just put a little 1/2 on that branch. The probability that I'll get tails is going to be the same, 1/2. Then you have to think about how many balls are in each of these. So to get a blue ball, it's 1 blue ball out of 3 total balls. And to get a red ball would be 2 out of 3 because you have 2 red balls out of the 3. For this one, you have a total of 4 balls. 3 of them are blue. So 3 out of 4 would be the probability of getting a blue ball here. I know, don't think it. And red is going to be 1 out of 4. Alrighty, that's a myth, by the way. Just for all you girls, that's a myth. Alrighty, then in order to figure, after we get the probabilities on each branch, we're going to use the multiplication rule to find the probability of getting heads and the blue ball. So we're going to take 1/2 times 1/3 and find the probability of the blue ball given the heads. Boy, this is nasty. So 1/2 times 1/3, remember you multiply straight across, you get 1/6. And all I did is went along those branches and multiplied them. To get the red, given the first toss being heads, I'd have 1/2 times 2/3, which gives me 2/6. And to get a blue ball, considering you have a tail, you're going to have 1/2 times 3/4, which would give you 3/8. And I go along here 1/2 times 1/4 to find the probability of that guy. One thing you want to see is 1/6 plus 2/6, that's 3/6 or a half. 3/8 plus 1/8, that's 4/8 or a half. A half and a half is 1. It'll always work out that way. So now finally, they want you to use the addition rule since a red ball can be obtained from box 1 or box 2. So the question asks us, what's the probability of picking a red ball or of getting a red ball? So you could have a red ball here or a red ball here. So you're going to add those two. This guy right here and this guy right here. Probability of red given this toss, probability of red given this toss. So we're going to add those two together. Probability of red box 1 or box 2. 2/6 plus 1/8. Ah, fractions. Woo, buddy. So we need to get a common denominator, which is going to be 24. So we'd have 8 out of 24 plus 3 out of 24, which would give us 11 out of 24. If you don't remember your fraction rules, I'll show you how to do it on the calculator. No problem. Easy peasy. Again, the sum of final probabilities will always equal 1. That's if you add these brown fractions over here. They should all add up to 1. And that's it. Clear as mud? Let's move along. Caution. When applying the multiplication rule, always consider whether the events are independent or dependent and adjust your calculations accordingly. I saw this little flow chart and I thought it was good. When you're trying to apply the multiplication rule, we're starting out. The first thing you say, we're going to try to do the multiplication rule because we're finding the probability of A and B. The first thing you ask yourself is, are they independent? If they are independent, you just multiply probability of A times probability of B. If they are not, that's when you have to bring in the probability of A times the probability of B given A. You have to adjust that second number. Alrighty, that was not in your notes. That's just more for your money today. Derive the identity for conditional probability for multiplication rule 2. What they want you to do is solve for probability of B given A. So all you're going to do is divide both sides by probability of A, and that's all there is to it. So it cancels out the PA, probability of A, and here's your conditional formula. Probability of B given A is probability of A and B over probability of A. When would you use this? When they actually tell you what probability of A and B is. Otherwise, you use the other thing. It kind of gets confusing with the formulas, but hopefully with practice you'll see when to use what formula. Let's look at this. So here you go. Here's a box again containing black and white chips. A person selects 2 chips without replacing them. If the probability of selecting a black and white chip, see they gave us that probability, 15 out of 56 is that one. And the probability of selecting a black chip on the first draw is 3/8. Find the probability of selecting a white chip on the second draw, given that the first chip selected was a black chip. That's what we're looking for. We know the probability of getting a black and a white is 15 out of 56. And the probability of getting the black chip just itself is 3/8. So we can put both of those in there. Now, this is just a big division problem. 15 out of 56 divided by 3/8. Remember, when you're dividing fractions, flip the second guy and multiply. So you're going to have 15 over 56 times 8 over 3. And I would probably cancel the 3 with the 15. That'll give me a 5 there. And then 8 goes into 56 7 times. That's just a little example of cross-canceling. Then you multiply straight across. 5 times 1 and 7 times 1. So you end up with 5 7s, hence the probability of selecting a white chip on the second draw, given that the first chip selected was black, is 5 7s. Bada boom, bada bing. It's just a matter of knowing where to plug these guys into those formulas. Alright, the probability that Sam parks in a no parking zone and gets a ticket is 0.06, and the probability that Sam cannot find a legal parking space and has to park in a no parking zone is 0.20. So here you see the and right there. So the probability that both those happen is 0.06. And the probability that he can't find a place and has to park in a no parking zone is 0.2, and you just divide those, you'll get 0.3. Hence, Sam has 0.3 probability of getting a parking ticket. You know, I got a parking ticket at the zoo once. I don't know. They are really sticklers there. All right, a recent survey asked 100 people if they thought women in the armed forces should be permitted to participate in combat. I say no. No, I don't want to go get shot at. The results of the survey are shown. The respondent answered yes, given that the respondent was a female. That's what we're looking for. Now, this one I think they confuse a lot because there's an easy way to do this. You can see the answer to this right away. It says the respondent answered yes, given that the respondent was a female. That's 8 out of 50. Boom. The respondent was male, given that the respondent answered no. So you look at all of these and you would have 18 out of 60. So you can get it just from this table, but let's humor them and do it the way the book went through it. So the probability of a yes, given that they're a female, you go with the probability you're female and you say yes. Okay, you guys, dirty minds, is going to be 8 out of 100. That sounds about right. So 8 out of the total respondents. The probability that you are a female is going to be 50 out of 100, half and half. And you can flip the second guy and multiply, but basically these hundreds cancel out and you get 8 out of 50, which is 4 out of 25. For the next one, which is what I said right here, 8 out of 50. So that's how, well, if anything, it confirms that the formulas work. Probability that you are a man, given that you said no. So the probability that you said no and you're a man, that rarely happens. You can look up here, probability that you're no and a man, I believe is 18 out of 100. 18 out of the total responders. And the probability that you say no is going to be 60 out of 100, because you had 60 people say no out of 100 respondents. Flip the second guy and multiply, the 100s are going to cancel out and you get 18 out of 60. But remember, if you're logical, a lot of these, you can figure them out. 18 out of 60, bada boom, bada bing. Reduce that to 3/10 and you've got it. There's a lot of examples on these in there. But don't you love my color coordination? All right, complements. The probability of at least one. Okay, now we're getting to the last little part. At least one is equivalent to one or more. When you are finding this, we're going to use the complements. And I know that this isn't on your notes, but I wanted to kind of explain it before we get to it. So when you do this, the complement of getting at least one item of a particular type is that you get no items of that type. The complement of it. So the complement of getting at least one, that the complement would be getting none. So you could think of it this way. To find the probability of at least one of something, calculate the probability of none and then subtract that from one. That's how we get the complement. And let's see how this works. You can use this multiplication rule, yada, 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 at least. Here's the first one we have. A game is played by drawing 4 cards from an ordinary deck and placing each card after it's drawn, replacing each card after it's drawn. Find the probability of winning if at least one ace is drawn. So what we're going to do is say no aces are drawn. So E is our event, at least one ace is drawn. The complement of E is going to be no aces are drawn. So when we do this one, the probability of the complement of E is going to be 48 out of 52, 48 out of 52, 48 out of 52, 48 out of 52. There's the complement. How do you get 48? Because there's 4 aces in a deck and there's 52 cards in the deck. So it'd be 52 minus 4 is 48. So this would be no aces drawn, you got a 48 out of 52 chance, and since we're doing 4 picks and we're replacing the cards, that would be our probability. I'd go ahead and reduce those, 12 out of 13, yada, yada, yada. You end up with 20,736 over 28,561. Yes, I'd probably go to a decimal at this point. Now remember, this is the probability you're not going to get any aces. So to find at least one, we just subtract that from 1. So the probability of we're going to get one ace, at least one, is going to be 1 minus P of the complement, P of that. So probability of winning, 1 minus P losing. So it's going to be 1 minus this whole big fraction. I'd go ahead and put it as a decimal, 0.27. So that's kind of interesting. Hoping you're following that. So let's look at this next one. A coin is tossed 5 times. Find the probability of getting at least one tail. This one, it doesn't really matter. But it's easier to find the complement of the event, which is all heads, and then subtracting that probability from 1. So at least one tail is going to be 1 minus the probability you get all heads. So we're going to have 1 times 1 half, 1 half, 1 half, 1 half, 1 half. You multiply straight across and you get 1 minus 1 over 32, because you multiply all the way across. And if you subtract that, remember 1 is the same as 32 over 32. 32 minus 1 is 31. So that's it. And hopefully that helps you. I want you to try this one with the neckwear association and see if you understand about the complementary events. It's kind of set up for you. They give you the 3% up here, so I think you can kind of figure that one out. Now, you can use similar methods to solve problems involving at most, and we'll get to that later.